Welcome to The Explainer. Today, we're unpacking a master's-level engineering thesis that completely tackles the future of uninterruptible power supply systems and predictive AI. We are looking at some seriously smart engineering today, basically bridging the gap between raw physical power hardware and highly advanced machine learning algorithms. If you've ever found yourself wondering how modern systems manage to charge massive battery arrays without just wasting tons of energy as heat, or, how they know exactly when a battery is finally going to die, you are absolutely in the right place.
Okay, let's dive right in with a massive hook. The prototype we are exploring today achieved a staggering 95.22% power efficiency. Now, in the world of power electronics, hitting an efficiency number over 95% is literally a game changer. It means that almost all of the electrical energy being pulled from the source is successfully making its way into the battery, with less than 5% being lost as waste or heat. So how exactly did the researchers pull this off? Well, that's exactly the journey we're going on today.
To understand exactly how they hit that incredible number, here is our roadmap. We'll start with the battery charging challenge, move into why we use LLC Resonant converters, look at designing the physical hardware, simulate the circuit, and finally, end with predicting battery life using AI.
Let's start right in with Part 1, the battery charging challenge, and how we overcome switching losses.
So, historically, engineers have faced a really tough dilemma. To shrink electronic components down, you have to switch power on and off incredibly fast. But doing that, it creates massive energy loss in the form of heat. With conventional series resonant converters, if your load is light, meaning the battery doesn't actually need much power at that specific moment, the system practically needs infinite frequency just to regulate the output. On the flip side, parallel resonant converters waste a massive amount of energy just circulating current within the system itself, which makes them completely impractical for high-power UPS battery charging.
Which brings us nicely to Part 2, why LLC resonant converters step in as the high-efficiency hero of our explainer.
This specific topology gracefully sidesteps those historical issues we just looked at. It handles wide load variations beautifully and does so with only a relatively small variation in its switching frequency. The absolutely crucial point here is that LLC converters can achieve zero-voltage switching over the entire operating range, and that is the exact magic that enables that 95% efficiency. In typical circuits, parasitic elements like leakage inductance are considered a huge nuisance, but the LLC converter actually utilizes these parasitic elements to softly commutate the switches. It's kind of like electronic judo, using the system's own weight to its advantage. By switching the current when the voltage is exactly at zero, you virtually eliminate those switching losses and dramatically reduce electromagnetic noise.
Moving on to Part 3, designing the physical hardware. It's time to turn all this theory into a real working PCB. This is where the theory actually hits the workbench. An uninterruptible power supply battery requires incredibly smooth, quick, and highly regulated charging. The goal here was to transform a heavy 400-volt DC input into a tightly regulated 48-volt 3.1-amp output to safely charge a 4x12-volt battery array. The source material lays out this dense, highly mathematical 7-step design procedure. To pull it off, you have to calculate the absolute optimal ratio between the magnetizing inductance and primary side leakage to find the perfect voltage gain. For instance, the researchers calculated a very specific 35:8 turns ratio for the transformer to perfectly step down that massive input voltage safely and efficiently. To execute this design, the engineers used a highly specific toolkit, packing it all onto a compact 10x10 centimeter PCB. They paired an FSFR power switch, which handles the heavy lifting and actually cancels out common mode noise internally, with a TSM 1011 controller to keep the battery safe. That controller handles both the constant voltage and constant current modes needed to ensure the massive battery array charges exactly how it's supposed to.
All right, Part 4, simulating the circuit to completely validate the math.
Before even thinking about soldering a single physical component, the entire half-bridge LLC resonant converter was tested in PSIM and MATLAB Simulink. Building physical prototypes is expensive and incredibly time-consuming, so running the math through simulation ensures it holds up in a virtual environment first. Notice how they purposefully set the switching frequency slightly higher than the resonant frequency. This firmly placed the converter in region 1 to absolutely guarantee soft switching. The math dictated a resonant frequency of 110 kHz, but by intentionally turning the switching frequency up slightly to 115 kHz, the engineers ensured that the intersection area between the voltage and current of the MOSFET was minimized.
This intentional offset is exactly how they achieved that beautiful zero-voltage switching we talked about earlier.
And the simulation was a massive success, delivering 47.67 volts and 3.07 amps. That is nearly identical to their theoretical 48-volt target. The theoretical calculations and the software simulations aligned almost perfectly. It basically proves that their step-by-step methodology to utilize the LLC converter to step down that 400-volt input worked absolutely flawlessly.
Now we transition to Part 5, Predicting Life with AI, the brains behind the brawn.
Having a highly efficient physical charger is really only half the battle for a UPS system. You also need to know, with absolute certainty, the health and the expected charge and discharge times of your battery array. Using Python, the researchers fed 4 specific data points from Tescom batteries into 10 different regression models to predict this behavior. They looked closely at the discharge current, the battery's current percentage, the ambient indoor temperature, and time. Before feeding all that to the AI, they used min-max normalization to clean the data, basically transforming the minimum values to 0 and maximum values to 1, so the algorithms could actually digest the patterns effectively.
Validation testing revealed something pretty cool. While linear and XGB models performed perfectly well, the random forest model was crowned the absolute winner. The researchers didn't just guess which AI model to use. They ran the data through everything from support vector regression to k-neighbors. But random forest, which builds a whole multitude of decision trees and averages them out, proved the most reliable. It had the lowest root mean square error, meaning the tightest margin of error at roughly 67.8, and a phenomenal R2 accuracy score of 0.9959 right out of the gate.
But this also builds a really fascinating cautionary tale about machine learning. You might think more complexity always equals better results, right? Well, if you increase the polynomial degree too much, the AI basically just memorizes the training data perfectly, but fails completely when it tries to predict new, real-world data. It's like memorizing an answer key for a test, but having no idea how to actually do the math. They discovered that while a 6-degree model gave way better estimates than a 2-degree model, pushing the degree too high mathematically overfits the data and ruins the prediction. 6 degrees was the absolute sweet spot.
By applying an optimization and variable importance algorithm to that winning random forest model, they pushed the prediction score to a near-perfect 0.9973. They took an already winning model and managed to squeeze even more accuracy out of it. The root mean square error actually dropped from over 67 down to 55.4. This means the system can accurately predict exactly how long a battery with a known charge rate can be discharged under specific load and temperature conditions.
So, when you combine a 95% efficient physical charger with an AI that perfectly predicts battery decay, it leaves us with one incredible question to ponder. How will this redefine the lifespan of every single electronic device we own? Think about the implications for a second. We've seen how utilizing an LLC Resonant converter entirely eliminates switching heat, and we've seen how a random forest regression model can perfectly map out a battery's life cycle. It is a powerful synthesis of hardware and software that points to a future where our critical backup systems are not just highly efficient, but incredibly intelligent. Thank you so much for joining me on this deep dive, and keep questioning how the technology around you actually works.